that we gave is just any collection of things with any common property, no matter what it is. So in the axiomatic set theory, we'll put a limitation on our language. So we'll just allow sets to have properties that can't be described in the mathematical formal language. So if you cannot describe that property in mathematical formal language, this set cannot be formed. And the reason for this is to avoid the semantic paradoxes. So last time we talked about the semantic paradox. So this arises because of the set of words that can't be described in less than 20 words. So this was the problem and caused the what we call semantic paradoxes. In order to avoid this paradox, mathematicians started to put abstraction on language. So instead of just using any property or using any statement as a property, they decided to restrict what properties can be used and decided to restrict them to properties that can be described in formal language. So properties that can be described in formal language are like there exists something or something like that. So less than, greater than, and all the logical operators can be used. But a statement like words that can be described in less than 20 words cannot be represented in the formal language of mathematics. It does not have a symbol to describe that. And so if it does not have a symbol in mathematics, it cannot form this set. And while this solution might sound disturbing, at least from a philosophical sense, it serves the mathematical purposes very well, actually. So is this clear, or are there any questions around this point? Okay. So the other kind of paradoxes were the logical paradoxes, and this includes, and the most famous would be the Russell's paradox. So if we remember, the paradox went something like the set of all sets that do not contain themselves. So in order to avoid this paradox, we are going to restrict the properties. So what kind of properties can form a set? Because this paradox uh, raised because we just had a set that is very big. It just included all the sets that do not contain themselves. So if we could restrict the properties through which we can construct sets, then this paradox just vanishes. So in order to avoid Russell's paradox, we have the first solution, which is the axiom of selection. So the axiom of selection simply says that properties do not form a new set but select from a pre-existing set. Or in the formal definition would be, let if we let A be a set and let Px be any statement about x. So using this statement, we can only select from another set in which A belongs, but we cannot form a new set. So basically, axiom of selection is literally what it sounds like. You cannot create a new set, but you can select from a pre-existing set. Um, and so, how this how this particularly solves Russell's paradox. So, if we give a formal expression of Russell's paradox in naive set theory, it goes something like S equals x such that x does not belong to x. So here it just said the same as saying set of all sets that do not contain themselves. So that's just expressed in the formal language. S is the set of all x such that x does not belong to x. And so the problem was asking, does S belong to S or not? So if we assume that yes, so if we assume that S belongs to S, this simply implies that S does not belong to S from our rule here, or from the property. And if we assume no, so if we assume that S does not belong to S, this would imply that S belongs to S because it admits to this property here. So in both cases, we reach a contradiction. So is this point clear, or is it still harder to understand? Okay, so is there any question around this point?
No, this makes sense. Yeah.
So if we apply the axiom of selection, this transforms into S equals x belongs to A such that x does not belong to x. So why? Because in the axiom of selection, we decided that you cannot form a new set, but you can select from a pre-existing set. So this pre-existing set here is A. So here, instead of S equals x such that x does not belong to x, it becomes S equals x belongs to A such that x does not belong to x. So again, we have the same problem, which is, does S belong to S or not? So we will going to first assume yes, that S belongs to S. this would imply that S belongs to A and S does not belong to S, because here it admits to the two rules here, that X belongs to A and X does not belong to X. And so here we reach a contradiction. So if we assume that yes, S belongs to X, we reach a contradiction. But however, if we assume no, then we can ask whether S belongs to A or not, right? Because here, if S does not belong to S, then maybe S does not just belong to A. And so if we assume that S belongs to A, then S belongs to A and S does not belong to S would imply that S belongs to S. So you can just simply look back, S belongs to A, and it admits to the rule that S does not belong to S. So it would belong to S, which is a contradiction. However, if we say that S does not belong to A, this simply would not give rise to any contradiction at all, because here it does not even admit to this rule. It does not belong to A. Is this point clear, or is it harder than before?
So with this new definition of sets or
Is there
classes,
any question about?
we don't have a paradox. We can just answer the question. No, S does not
We still
belong to
did not
S.
reach. If S does not belong, so after I reach the point of assuming that S does not belong to S, I can ask whether S belongs to A or not, right? Because maybe S does not belong to S, but it belongs to A. But here I'm asking whether it belongs to A or not. Okay. So if it does not belong to A, then this would not give rise to any contradiction at all. Does this make any sense, or should I explain it?
Can you wait 1 second before you move on?
So we're saying that one set equals or belongs to S. So like the set S is equal to the set or is a part of set S. Like what the problem
Yeah.
is.
If S belongs to S, okay, so
Uh-huh.
this implies that S belongs to A,
Wait,
and
so
it
S
also
is
implies
the
that S does not
whole
belong to S.
sorry. So then what is like X and A, those are also different sets.
Yes, so A is a, so you can imagine that S is inside A, or I'm asking whether it's inside A or not, right? So
Uh,
S is just the set of elements X that belongs to A, and that
mm-hmm.
and the X does not belong to X, right?
Mm.
So if S belongs to S, then I know for sure that it belongs to A, and I also know that it does not belong to S because it admitted to the rule, right?
Oh, okay, I see now. Okay, this makes sense.
This will
Okay.
be a contradiction.
Yes.
Whether in the second case, if S does not belong to S, I can ask whether it belongs to A or not. Okay, so if it does not
Mm-hmm.
belong to A, then there will be no contradiction because
Mm.
this is the second rule. So simply what I'm saying here is that I'm saying that there is no S in A such that X belongs to S belongs to S. Okay,
Mm.
so I'm saying
Perfect.
inside A there's no X that belongs to X. That's what I'm saying.
Yes.
That's
Got
why
it.
it's different from the first case where this was the simple rule. So that's why it's
Mm-hmm.
different. Because here I'm asking about a rule inside a set. So I'm saying it does not apply inside the set.
Mm.
And that's why the axiom of selection solves the problem.
Okay, so we're saying that A is a separate type of set that S or X is not equal to or is not a part of.
Yes, exactly. What I'm saying is that inside the set A, there is no element that belongs to itself. That's what I'm
Mm-hmm.
saying. There's
Mm.
no element inside A that belongs to itself.
Mm.
So
Okay.
that's what I'm saying.
Mm. I get it.
So should I go on or wait?
Lisa.
Okay. Should I go on?
Okay. Yeah. Yeah.
So later then they decided to form a better solution than the axiom of selection, which is called the class axiom. So the formal definition, it says that if P of X is any statement about an element X, then there exists a class which consists of all those elements which satisfy P of X. So here so this is different from the naive set theory. In naive set theory, we had that a set is just the collection of elements that have the statement P of X. This time, instead of defining a set, we're defining what we call a class. Okay, so we are defining that there is something that we call a class that has all the elements that contain P of X. So I don't only have, so I can do more than just selecting. I can create something, but not a set, a class. Okay, so the difference, so the definitions is that we have something called a class. A class is just any collection of objects having a common property. Okay, so that's our old definition of a set. We now call it a class, but then now we make a distinction between two kinds of class. An element is a class that can be described with inclusion. So I can say X belongs to that and X belongs to this. So I can describe an element with the property of inclusion. On the other hand, I cannot describe a proper class with inclusion. So a proper class cannot belong or be a subset of anything. Is this point clear, or should I re-explain it, restate it?
Wait, could you re-explain what a proper class is again?
Okay, a proper class is just any class that cannot be described with inclusion. Okay, so we describe elements with X belongs to S or X does not belong to S, right? So that's what we do with elements. What I'm saying that I'm defining something that I call proper class that does not admit to this rule. It cannot be described with inclusion. So simply, a proper class does not belong to anything.
Okay,
Okay.
so if like X is a proper class, then it won't belong to any other element or any other class, but it can
Okay.
still be a
Exactly.
part of. But can it still be a part, or can it still have an element in it?
It can have things. Yeah, it can have elements in it, but it cannot be part of an element. Yeah, it cannot be subset of a thing, but it can have elements inside it. Okay, so why this is better than our axiom of selection? Because in our axiom of selection, um, I cannot create a new set. I can only select from a pre-existing set. I cannot create anything new. Whereas in the class axiom, I can create a class. I can create something called a class by any common property. And that's why it's different from the axiom of selection. So the axiom of selection, basically, you have a set and you select parts of it. You cannot create a new set out of nothing. Whereas in the class axiom, I can create a class. I can just have this common property and make this thing happen. So is the distinction between the two axioms clear? Or should I go on?
Can you explain the difference thing again?
Okay, so the axiom of selection says that properties do not form a new set, but select from a pre-existing set. Okay? So is this part clear? So you have the set and you choose properties from within it, inside it. For example, you have that set of all cats, and you cannot form a new set. You can just say, I will select from these sets the cats that have black fur, for example. But you cannot create a new set. You can only select from a pre-existing set. So is this definition
Oh,
clear?
yeah. I think. Wait, can you give sorry, I like just jumped in. Can you give like an example of the axiom of selection?
Okay. Okay, can you repeat this again?
Oh, I said can you give an example?
Okay, yeah, as I said, like, like if you have a set of all cats, you can select properties from within this set. So you can say, I will select all the cats that have a black fur. Okay, so, but wait, are you asking about an example for class axiom or axiom of selection?
Wait, no, that was good. That was good.
Okay, so that's the axiom of selection. You can exist from a pre-existing set. You can create a new one. Whereas in the class axiom, I can create a class with of shared common properties. So I don't have to select from a pre-existing thing. I can create an entirely new thing. So is this point clear?
Can you quickly explain again what inclusion means in that context?
Okay, so inclusion means that an element is inside another one, right? So, like a black cat is inside the set of all cats, so it's an element of it. That's what inclusion is. Inclusion is that something is inside another thing, right? So that's what inclusion is. A proper class is not included in anything, okay? But things can be inside it. So a proper class can have things inside it, but it cannot be inside anything.
So question.
At
So
this
if
point,
there's
it's clear. Or
something so if there's something inside a proper class, then it's considered an element. That's it. Like it doesn't matter what class it's
exactly,
inside. If it's
it
if
cannot
it's
be a proper
anything
class. So
inside a
you
class.
cannot have a proper class
Okay.
inside a proper.
Aamen, just so you know, I think there's like a bit of a lag
So
for when we say something and when you hear it. So also just so everybody knows, if it feels like he starts talking before you finish, that's just because there's a bit of a lag. Yeah. Are we good to
yes,
move on?
sorry, I'm really having a lag. So I'm sorry for
Don't worry about it.
again.
Oh, I said don't worry about it.
Wait,
So should I go on or
I
should
just
I?
want to like make sure. Wait, sorry.
Uh-huh.
Okay, it's like kind of hard to hear. So like so proper class is like the paradox we were talking about last time, where it's like a class can be described as an element within that class. It's like that paradox is cannot be possible with a proper class, right? Is
Exactly.
that okay? Okay, and then like elements, a class that can be
So,
just. I like kind of heard I heard like half of your explanation. I'm so sorry. Can you repeat it again?
okay, so and we are now defining something
Like
called a
what?
class, which is so basically a class is just any collection of things that have a common property. A class have two kinds: a proper class, which cannot be described with inclusion, and an element, which can be described with an inclusion. So in other words, a proper class cannot be inside a thing. It cannot belong to anything. However, an element can belong to a thing. So, for example, all the elements inside a proper class cannot be proper classes, okay? Because a proper class does not belong to a thing. So did you
Okay.
get that? Or?
Oh yeah. I got it. Thank you.
Cool. So now applying the class axiom to, so we're going to apply the class axiom to the paradox to see how it vanishes. So the formal definition would be S equals X such that X is an element and X does not belong to X, right? So now instead of the in the original paradox, we had that this is just the definition. This is the definition of our set. S equals X such that X belongs to X with no restrictions at all. However, after the class axiom, the definition changed of our set. So it's S equals X such that X is an element and X does not belong to X. Okay, so again, the same question: does S belong to S or not? So if we say yes, that S belongs to S, then if we say that S belongs to S, then it's described by inclusion. Then it's an element. And since it belongs to S, then this rule applies to it, so it does not belong to S. So here it's a contradiction. However, if we say that S does not belong to S, I can ask, is S an element or not? Right? Because in the beginning, when I said that S belongs to X, to S, then I already described it with inclusion. Then I'm saying it's an element. So, so if it's an element and S belongs to S, this would imply that S does not belong to S, which is a contradiction. However, if I say that S does not belong to S, then I can ask whether S is an element or not, right? So if S is an element and S does not belong to S, this would imply that it belongs to S because it admitted to the two rules, which would be a contradiction. However, if I say that S is not an element, then S is just a proper class and cannot be included in this set at all. So in this case, there will be no contradiction at all. So the only contradiction will arise if I say that S is an element, but I'm saying that S is not an element and hence does not admit to inclusion. So is this point clear, or is it clear why the paradox vanishes here? should I re-explain any part of it?
Sorry, I forgot I was muted. Can you guys see this?
Yeah.
Okay. Does it kind of make sense what Amen's logic was? Like, you're basically testing out different theories, and then we can see with the class axiom, we can reach a spot without a contradiction by saying that S is not an element of S and S is not an element. Is that kind of making sense?
Wait, no, only the last one works, right?
Yes,
Where
only
S
the
is
last
not
one
an
works.
element. That's it.
Yeah.
Yeah.
This path has a contradiction, this path has a contradiction, this one doesn't. So with the class axiom, we're avoiding Russell's paradox.
Should I re-explain it, or is it already clear? So the problem in Russell's paradox is that x cannot belong to x and it cannot not belong to x, right? But if I say that x is not even an element, so it does not even admit to inclusion. So it's just meaningless to say that x belongs to anything or does not belong to anything, right? So if I just define S as a proper class, right, so there will be no contradiction. Because here after the class axiom, the conditions, we have two conditions, that x is an element and x does not belong to x. But I'm saying S is not even an element. So is this point clear?
Wait, was it just me or did he cut out for like a couple seconds?
No, I was able to hear him fine.
Really?
Okay. So
Okay.
let me repeat this. So here after the redefinition of Russell's paradox, the conditions are that x is an element and x does not belong to x, right? But if I say that S is not even an element, then it's a proper class, right? So this whole idea of inclusion does not apply to it, and so the paradox just vanishes. So, so if S was an element, then there will be a problem. But if it's not an element, the paradox will vanish, right? Or is it clear why it vanishes? Or
Wait, so for class axiom, all we're saying is that X is an element of X. No?
no, in the class, in no, yes, we are adding this restriction to the rules of S. So adding
Mm-hmm.
another restriction for the paradox to occur, right?
This
So if
Mm.
change.
simply S is not an element, so this whole idea does not apply to it.
So where it says that X and then it has the semicolon and X is an element, right? All we're saying is that it's not an element. Then that
So yes, we are
works.
saying it's not an element.
So
It's
we're
just a proper class, so it
okay.
cannot be described with inclusion. Inclusion
Mm.
is meaningless for a proper class.
Okay. I got it.
So is the idea clear, and is the logic behind this whole thing clear? Or so is the logic clear, or should I explain anything?
I think, again, if anybody has questions, you can always ask us because these are concepts that are normally taught to college students, but they're really useful to try and understand early. So if you have any questions, please don't be afraid to ask. That's the reason we're here.
Okay. Okay. So we are going to review the definitions now in the axiomatic set theory. So first, a class is just a collection of elements sharing any common property. Okay, element is a class that can be described with inclusion. A proper class is a class that is not an element, and then these are just the same definitions of the naive set theory. A union B, the elements in A or B, A intersection B, the elements in A and B, A difference B, A complement, and the and A that sign B, which means elements in A and B, but not in A intersection B, right? So this is just basically A union B, the difference A intersection B. So the elements in both of them, in any of them, but not in both.
Amen, if you click through the animations, you should be able to see, there you
Okay.
go, it's an example.
So, so I so is the example clear? Or
So that's one example of a union. If you click again, you just want to click again. There you go. So, oh, okay.
so that's intersection.
Mhm.
Okay. So that's the difference, A difference B. Okay, so that's A complement. So that's all the elements in the universe but not in A. Are these symbols clear or is there any difficulty in them or something? And that's the asymmetric difference B. So the elements in A and B but not in the intersection. This sign is just the same as this one. Okay. So you can use any of these. So are these concepts clear or do they need further clarifications? Something. Okay, so we'll jump to basic definitions in and the axioms of axiomatic set theory. So first the axiom of extent. So first from the first thing that we need to define is what is the meaning of equal. Okay, so I want to say what do I mean when I say A equals B? Okay, so this is just the formal notation. I will just go through it. So this is just for all x. Okay, so this simple means for all x, for any element x. X belongs to A implies that X belongs to B, and X belongs to B implies that X belongs to A. Or, or in just a shorter version, for all X, X belongs to A if and only if X belongs to B. So simply what this means, in order to have two sets equal, they must every single element in A must be also in B, and every single element in B must be also in A. Right? So is the logic behind this idea clear? So when I say that two sets are equal, what I'm saying that every element in A is in B, and every element in B is in A. So this okay. So this is an example of A equals B. So here all the elements in A are included in B, right? One is in both, two is in both, and three is in both, right? Here, A and B are not equal. All elements in A are in B, but not all elements in B are in A, right? So there are unique elements in B. So I cannot say that A and B are equal.
Oh, by the way, there are some formatting things that we didn't introduce you guys before in case you're not familiar with them. So you can see in the definition of axiom of extent, there's a upside down A thing. That's basically saying for every element A, if that element is in A, then that element is in B. So for every, sorry, I messed that up. For every element X, if that element is in A, then that element is in B. So that little upside down A thing, when we're translating from mathematical logic to English, it just means for every element followed by whatever element we're talking about. We covered the implication symbol last time, but and we covered the and statement last time. We didn't show you guys this way of defining sets before, where if you look at the examples, you can just see things covered in brackets. That's basically just saying we have this really, really small set that just contains these three elements separated by commas. That's it. When we define things in order like that, in brackets like that, the order doesn't matter. We're basically just saying this set has these elements in it. So yeah, if you guys haven't seen any of this notation before, just let us know and we can clarify that.
Okay, so is it clear why A equals B in the first example and not in the second example? So it's not sufficient to only prove that an element in A is in B, but you have to prove that an element in A is in B and every element in B is also in A, right? You have to prove that there are no unique elements in any of these two sets. So then I will find subclasses. So A is a subclass of B. The definition of that would be for all X belongs to A implies that X belongs to B. So this is different from the equality. Um, in the equality thing, X belongs to A implies that X belongs to B, and X belongs to B implies to X belongs to A. Whereas in the subclass, I'm only taking the first part of the definition. For all X, X belongs to A implies that X belongs to B. Right? So here in this example, A is a subclass of B because all elements in A are in B, right? In the second example, also A is a subclass of B because all elements A are also still in B. So in order to say A is a subclass of B, you only take the first part of the definition of the equality. So if you compare this to the equality, so if you compare this definition to the equality one, you'll find that there is an extra condition of the equality. Okay. So is the idea of subclass clear or?
As a bit of an example, two equal classes are like the set of all numbers and the set of all numbers are obviously equal because every single number is also a number. But for subclasses, you can say the set of all even numbers is a subclass of all numbers because every even number is a number, but it doesn't go the other way. Not always. Like, it's not like the set of all numbers is a subclass of the set of all even numbers because there exist numbers that aren't even. So does that kind of make sense as an example?
Okay, so in the second example, B is not subset of A because there are elements in B that are not in A. Okay, so B is not subset of A, whereas a subclass. B is not a subclass of A, whereas A is a subclass of B. Okay. Then there are strict subclasses. Okay, so strict subclass used by this symbol. So it's just A is a subclass of B and A is not equal to B, right? So in the second example, here A is a subclass of B and A is not equal to B. So we say that this case is true, right? Whereas in the first example, A is a subclass of B, but A is equal to B also. So this would not be true. A is not a strict subclass of B. It's just like the relation between less than and less than or equal, right? So this is just like the less than or equal. So here, if you have less elements and all the same elements exactly, this works fine. It's just like the less than or equal. Whereas in this case, it's just like the less than only. So they cannot be equal. If they are equal, this thing does not apply. So is the difference between strict subclasses and subclasses clear or?
So going back to the earlier example, you can technically say that the set of all numbers is a subclass of the set of all numbers, like two equal sets. Another way to define set equality is that each set is a subclass of the other. But strict subclasses get rid of that difference. The set of all numbers is not a strict subclass of the set of all numbers because they're equal. The set of all even numbers is a strict subclass of the set of all numbers. Yeah?
Okay. So just a few exercises. So I think you should all think about this for some time because almost all the problems in set theory come in this form. So I think you have just some time to try to prove this idea that A equals B and B equals C implies that A equals C. So I think I will just give you a few minutes to think of it. So when you want me to show the answer, type in the chat that you want me to show it. So I just can know that you've finished solving the problem.
You guys want to see the answer now?
Yeah.
Okay.
Okay. So we have that A equals B and B equals C. So if we translate this into the formal um, language, th- also all this will imply that X belongs to A if and only if X belongs to B, right? Because this is the definition of equality. I just plugged in the definition of A equals B. So A equals B means that X belongs to A if and only if X belongs to B. And so if I use the definition of B equals C, I would have that X belongs to B if and only if X belongs to C, right? So these two together imply that X belongs to A if and only if X belongs to C, which would imply, which is the definition of equality actually. So this would imply that A equals C. So if you think of it, it just you just plug in the definitions, okay, and then you reach your result, and that's what you'll do a lot in set theory. So and you will use this implication a lot. So if you have A equals B and B equals C, this would imply just the definitions. X belongs to A if and only if X belongs to B, and X belongs to B if and only if X belongs to C. And this as a whole will imply that X belongs to A if and only if X belongs to C, which would imply that A equals C. So is the answer clear, or is there a problem in it when definitions were plugged?
I'm gonna show a slight. It's the same thing, just written out a bit longer. Oh my god, I keep on forgetting. I have to click it over here and over here. Can you guys see my screen?
Yeah.
Yeah.
Okay, so this is the same thing that Aamen was just talking about. We're taking that initial problem that we're given
Lisa,
and just
I think
splitting up what it
wait,
means.
well, can you all see Lisa's screen, or
You have
Yeah,
to
I can see
choose
it.
it. So you have to go to the view options and then press Lisa
Oh.
George screen.
Because there's multiple
Yeah.
screen shares right now. Oh, I don't know if this will be in the recording. I guess we're just gonna have to hope so. Anyways,
wait,
so
Wait,
Wait, no,
just
unless
should I stop
just
sharing so Lisa can?
yeah,
or no,
that would be better.
you should just spotlight Liza because then it will appear.
can you guys
Oh,
not
Lisa
see?
can spotlight.
Sorry, we're kind of new
So
to this
Lisa,
stuff.
I will stop sharing.
Spotlight self. Yeah.
I think I could not hear you, Diana. Can you repeat this again?
Oh. Wait, does my mic not work?
No, I can hear you. I think there's probably just a lag.
Um,
Oh god, maybe this double sharing thing isn't worth it.
So okay, so
I think
Lisa,
it's
so I think I have an idea. I think I can just finish the exercises, then you can explain them. You can share these later.
Mm-hmm.
So okay, so we'll just first go through my screen, and then after I finish, Lisa will share her screen and explain it then. So second exercise, we got A subclass of B and B subclass of A implies that A equals B. Okay, and also again type in the chat when you want to see the answer. so should I show the answer now?
Yeah.
Yep.
So again, like before, just plugging in the definitions. So A, subclass of B, just putting the definition is X belongs to A, implies that X belongs to B, right? So that's just the definition of A subclass B. And B subclass A is X belongs to B, implies X belongs to A. So these two together give me the definition of A equals B. Okay, so A subclass B is just this definition, B subclass A is just that definition, and these two together give me A equals B. So this is just, the whole thing is the definition of A equals B. So is the method that we are using clear, or is there a problem in the method that we are using?
Yeah, it's clear.
So a final exercise, I guess. Again, also type in the chat. See the answer. Okay, so I will show the answer. Also, like the last time, A subclass B and B subclass C, plugging in the definitions. So the definition of A subclass B is that X belongs to A implies that X belongs to B, and the definition of B subclass C is X belongs to B implies that X belongs to C. Which basically, so you have X belongs to A implies that X belongs to B, which in turn implies that X belongs to C, right? So this would imply that X belongs to A implies that X belongs to C, which is just the definition of A subclass C. So all of this would imply that A is subclass of C.
I think real quick, something that might make this, I'm just gonna try one more time for the iPad thing, and if it doesn't work, then it doesn't work. But something that might make this a lot easier to think about. First off, can you guys give like a thumbs up if you can see my screen at all?
It works.
Yeah. So do you see how there's like a Venn diagram? A, can't point at that. Okay, A is a subclass of B because every element in A is an element of B. And in the same way, B is a subclass of C because every element that's in B is also in C. And so naturally, A is a subclass of C because like you can see it in the Venn diagram, right?
Yeah.
Okay, cool.
Okay, so that's it, I guess. So is there anything that's not clear, or
Any of the
is there any question?
exercises or definitions or slides you want to go back to or anything like that?
Wait, can you send the slides in the Discord?
Yeah, I can just send the whole folder. Give me a sec.
So then we can see if there's any slide that we didn't understand.
Something that helped me sorry, I'm trying to do multiple things at once. Something that helped me learn this stuff was to make like a formula sheet of my own kind of thing. Do you guys think like instead of having to go back to these slides every time, that would be helpful?
Yes. Yes.
Hold up, let me get that link. Copy pasted the wrong thing. you go.
I have a question. Are we doing riddles next time?
Oh
Mm,
yes, sure. Yes.
Right. By the way, you guys are free to leave. Like I know it's a volunteering thing. You can leave whenever you want, but if you don't have any more questions, we're not going to keep you on for the extra 10 minutes.
Oh, so I think you can stop recording now.
Oh, that's true.